Alright, we've got a bit of a hum here, but what we're going to do right now is we're going to go through adding vectors by hand. When I say by hand, and I'm off camera here, we have here essentially having them by sliding them along a plane. I will let you know that the reason why you have been introduced to matrices and calculators and Wolfram Alpha and a number of other things is that when you get into the 3D work on this, it's hard to do it on a flat board, though historically that's done as well on screens like radar screens and the like. I also have given you technology in front of you here, and that we have a drafting board, but we will demonstrate then also how to do this by actually sliding triangles with their hypotenuse. So I'm going to run and grab a set square. Okay. This here is a very large drafting triangle. This is called a set square. It's 90 degrees, right? So it's got one side is 90 degrees to the other, and you're going to use this as often, or probably more often, than using a drafting machine. Though if you have room in your basement and you can negotiate with your spouse, you can't pass these things up. They're pretty nice. So you have now the concept of adding vectors, and we're going to start with the fact that when you're working on vectors, there is usually more than one vector type in a plane. So you want to get good at using, like you will in CAD, different colors. So we'll see whether this picks up as green, whether this one picks up as brown, whether this one picks up as blue, and we've got two shades of green. So you're going to often, when you're doing engineering problems, you're going to have more than one. Let's put this across. There's green. We'll see how that picks up. You're going to have more than one vector type on a plane. So for instance, you'll have one, perhaps, if you're doing torque calculations, you'll have one vector that will be the radial vector, or essentially the wrench, if you would, and you'll have one vector that is distance. So let's see if we can lay that out here on this board. So we're going to start with the fact that this is going to be distance, and this is going to be force, and in the end we'll use blue for torque. But the reality is, when you have distance and force vectors on a plane, the torque vector is actually always coming either into or out of, because of the simple knowledge that the cross product of any two vectors in a plane is the normal to the plane. Alright, so let's start with how we go about using this machine, just to add a couple of force vectors on a simple object. And so I'm going to go ahead and use this kind of dark green one for my object. And for now, I'm just going to make it this something object here, and we're going to apply a very typical problem, which would be this rock in a hard place. So I'm going to go ahead and keep using the green here. You know, you've heard the term between a rock and a hard place. Well, there's a rock. I'm going to run through the screen here now, and hopefully I'm going to make sure I'm hitting the record, and now I'm not even using my tools, so I better start using my tools here. I'm going to go ahead and now slide this over here and start to realize that a lot of these programs are set up something like this at 15 degrees. So that was an arbitrary angle here, but this right now is not an arbitrary angle. So this here is clicking up at 30 degrees. And so a machine like this is going to have a snap at 30, 15, at 30. Remember, at pi over 12, because there are 24 time zones on the planet. And now we have basically a thing. We now come to some definitions here, walking back and forth in the frame. So, force, right, is something that is a push or a pull. The force due to gravity would be something that we most use. It is weight. There are a couple of other important forces that you know, or to think about. One is the normal force, which is normal to the point of contact, and the other one then is the friction force, which is normal to the normal force. You can have electromagnetic forces. you have buoyant forces, but you have to start with the general sense when you do a free body diagram, and we're doing that in terms of adding vectors, is first what is touching that object. Once again, what is touching the object? And touching in this case would be the fact that there is a force that's everywhere on this object, but we can think about that force as being at the center of mass of the object. And that force has usually a definable or calculable value. And in this case, we're going to hope that our settings are set right. We're going to all of a sudden start very early. Going to go ahead and get my dark green. We're going to call this, in this case, X, and moving this over here, moving this down. We're going to call that X, and we'll call this, for this demonstration, we're going to call it Z. And I'm going to try to get pretty good. You're used to X and Y, but we're going to call this X and Z because in reality, gravity acts down Z. So we have a center of mass. Now that might not be the geographic center of that rock, what's between a hard rock and a hard place, but depending on the density of the material inside. But we have now a calculable direction. And I'm going to put that in as a light line there. So that there is the direction. It's called the line of force. We then also have two other calculable lines of force. If we can pick out that this is the point there and this is the point there, points of contact, and assuming no slipping and the like, we can now use our machine and kind of unlock it, if we can do that. I'm going to turn this, and we can set it as we slide it here so that we're at that angle, and then we can slide it up back and forth, left and right, to give a normal force. I'm going to slide that up. And we can now tell you that that, in fact, is the direction, right, of the normal. So we don't know how much the force is on that side, and we do not know the force on the other side, but we know its line of force because it is perpendicular to the point of contact, and the point of contact, of course, we get from looking at, I'm trying this through here with the machine, and those of you who really draft on these machines, of course, you're laughing right now because I'm not necessarily holding it that well. Now you learn to lock things. I think this will be the lock here. That's locked, so now I can go here, and we know that right here is the other line of force. All right, so we now have, effectively, we have three lines of force, and you'll see later through these points of contact that the center of mass, as this works, this would adjust so that you actually would go through the three forces, in fact, have to actually have, they have to be concurrent. If there is 1, 2, 3 forces, then those three forces actually have to be concurrent. So if you look at this one here or there, we get into a bit of a conundrum here with the drafting aspects of this. All right, so I'm going to continue through that, and we'll kind of draft this up and use a calculator or computer to fix it, part of it. But what I want to show you now is how you actually add vectors. First off, you have to understand that these three forces are going to be concurrent. This one, and this one, they have to be concurrent. So the reality is that as you get one of these known, if we assume that you know that force, then this one here is not going to be normal. It's going to actually have to be, this is a line of force, this is a line of force, this other one here, by definition, if it is only three forces, those forces have to be concurrent, so they have to go through the same point. And so the reality is, once we've got, if we know that this is frictionless on one side, and they're going to guess that you can go ahead and change this slightly, kind of playing around with that, you need to put that, if that is your point of contact, right, you know that that is the, this is the direction of that force. So now we have essentially three lines of force. This is a statement of fact. If a free body is subject to three forces only and it is stable, it is not accelerating, it is in equilibrium, the forces must be concurrent, which means they must go through the same point. So now we're going to go about and look at how we can solve this by adding vectors and doing some basic subtraction. So here's what we know. we know, and I'm going to now go ahead and use this in probably a poor way again. We're going to go ahead, we know that perhaps we might know the weight of that vector. So I've got scales on here and it's set up, so I am going to slide this and I'm going to make that vector as it would. I'm going to make it someplace like, that's 24. I'm going to say that the scale on here is 1 unit is 10 pounds. So I'm going to go from here down to 14, and that is that force. So I know this force, and vectors have what's called a tip and a tail. So that, if you notice, is the force vector. Now we also know that these other ones, we know their lines of direction, so we can show them here sketched. We know their line of direction, but now we can go about adding vectors by doing this. We can actually go off to the side here. We don't need to work on that, and we can slide parallel vectors. So I'm going to take that same, and I'm going to say this is now a representation of this whole thing. This is the free body. It is subject to 3 forces. One of the forces is straight down. We'll put that in here, and we can give it a value in a second. One of those forces is straight up and down. That's the weight force. Another one of the forces, and we'll see if we can kind of, another one of the forces going through that body, working with this, is we know its direction. Again, sliding it up. I'm going to run out of time here in a second. We know the other force is along that direction, right? And so if we lock this up, we can kind of slide this down, move it up and down. We can slide it over, so we know that's the direction of the other force, right? And that we can do the same then for this one here, which is a little bit easier to do. And we know that this is the direction of that force. Now we know their directions, right? What we're going to do in the next video is to realize that we can decide to do this. We know this distance here, we can mark that up, we can pick a direction home, and we can realize that we add vectors, tip to tail, boom, 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 and we have essentially the solution to our problem. All right, we're going to put this one out. We'll look at the conundrum here of the drafting, but realize that when we add vectors, we're going to add this vector, plus this vector, plus this vector, and then we transfer the vectors back. You add vectors by doing them tip to tail. If something is a 3-force system, the forces must be concurrent. Thanks for listening.